You ever see a headline or a title that's so packed with jargon it just feels like it's in a completely different language? Well, today we're going to tackle one of those head-on. We are going to take a seemingly impossible technical title and prove that with the right key, pretty much anyone can unlock it. Let's dive in. Okay, here it is. This is the actual title of a research paper from the IEEE. QLC, Programmable 3D Ferroelectric NAND Flash Memory by Memory Window Expansion using Cell Stack Engineering. Wow, I mean, that is a mouthful, right? It almost feels like a wall designed to keep people out. But what if it's not a wall at all? What if it's actually a roadmap? Let's find out. So where do you even begin with something like that? It is so tempting to just, give up, close the tab, and move on. But we're not going to do that. Instead, we're going to treat this like a puzzle. We'll find the corner pieces first, and then just build our way toward the middle. So let's go find that first piece together. Right, here's the trick to decoding anything complicated. You got to find an anchor. You just need one familiar term in that whole sea of jargon. So let's scan that title again and look for a word or a phrase we've probably all seen before. Once we have that, we can start building.
And there it is, flash memory. We all know this one. It's in our phones, it's in our USB drives, our cameras, our computers. The absolutely crucial thing to remember is that it's the type of storage that doesn't forget when you turn the power off. And that right there is our anchor.
To put that into perspective, just think about the RAM in your computer. That's like its short-term memory. It's super fast, but as soon as the power's gone, it's wiped clean. Flash memory, on the other hand, is the long-term memory. It's where your photos, your apps, all your files live permanently. Okay, so we've got our foundation, now let's build on it. So we're talking about permanent storage. But, the challenge is always how to fit more and more and more of it into a tiny little chip. And the solution engineers came up with was brilliant. If you can't build out anymore, well, you build up. Let's look at the next part of the title, which is all about how they built a kind of data skyscraper. That 3D in the title is, well, it's exactly what it sounds like. Instead of laying all the memory cells out flat on a single floor, engineers just started stacking them vertically. The genius of it is just so simple. If you run out of land, you build a skyscraper. This move massively increases storage capacity without taking up any more physical space. So if 3D is all about adding more floors to our data skyscraper, QLC is about making every single room in that skyscraper way more efficient. QLC stands for Quad Level Cell, and it's a technique that lets a single memory cell hold 4 pieces of information instead of just one. It's kind of like turning every studio apartment in your skyscraper into a 4-bedroom suite. The density just skyrockets. So let's just trace that evolution for a second. We went from a flat, single-story building to a towering skyscraper. And then we figured out how to make every single room in that skyscraper 4 times more efficient. That powerful combination, 3D stacking and QLC, is really the engine behind the massive amounts of storage we all have in our pockets today. Okay, so we've got the basic architecture down. Now we get to the really fun part, the actual breakthrough that this research paper is all about. These next few terms, they're the scientific heart of the whole innovation. This is the secret sauce. Ferroelectric. Now that sounds pretty intimidating, but let's just simplify it. Think of it as a new, special kind of building material for our data skyscraper. This stuff has really unique electrical properties that allow the memory to work faster and more reliably, which is super important when you're dealing with the complexity of QLC. It's the secret ingredient that makes the whole recipe better. Okay, next up, memory window expansion. Now think about this. If you cram 4 different pieces of information into one tiny cell, it's going to get crowded, right? It can get really hard for the chip to tell the difference between them. Well, this term is just a fancy way of saying the researchers found a method to make the signals for each piece of data much clearer and more distinct. It's like cleaning a really foggy window so you can see perfectly what's on the other side. And finally, cell stack engineering. This one brings us right back to our skyscraper. This term is really just about the specific architectural plan, the detailed blueprints, and the construction methods they used to build this new kind of memory chip with that new ferroelectric material. This is the how-to guide that makes the whole thing work. All right, we've done it. We've decoded every single piece of that puzzle. We started with an anchor we all knew, and we built our way up piece by piece. Now comes the payoff. Let's put the title back together and see the whole picture. And here it is. See, that title wasn't a random string of words at all. It was a story told in perfect order. It's about a way to program QLC, or 4-bit data, into a 3D memory structure. It's a new kind of flash memory using a special ferroelectric material.
And the big breakthrough comes from making the data signals clearer. That's the memory window expansion, which was all enabled by a smarter construction method, the cell stack engineering. Suddenly, it all just clicks into place.
So, after all that, what does that monster of a title actually mean? It means this. This research is about a new way to build a better, higher capacity flash memory chip. That's it. We've just translated all that intimidating jargon into one simple, powerful idea. Now, it's easy to look at something this technical and wonder, okay, but so what? What's the point? Why do scientists spend all this time on these tiny improvements? Well, it turns out there's a much bigger mission at play here.
This quote from IEEE, the organization that actually published the paper, really says it all. The goal isn't just to make a faster chip. The goal is to advance technology for the benefit of humanity. Denser, more efficient memory like this is what allows an AI to analyze medical scans right on your phone or a scientist to process huge climate data sets on a regular laptop. Every single piece of that jargon we just decoded represents a small but totally crucial step forward for all of us.
So, the next time you run into a wall of words that seems impossible to understand, just remember this process. Find your anchor, break it down piece by piece, and then put the story back together. You have the tools now, so the only question left is, what jargon will you decode next?